It's my pleasure to introduce this evening Professor Raya Zvigler, who is going to give us the webinar. Raya's first degree was in applied physics, and then he took a PhD in electronic and electrical engineering from the University College London. He is now Professor of Computer Science and Head of the Graduate School at Aberystwyth University. He has published over 300 articles in journals and peer-reviewed conferences and has attracted over £5 million in research funding. He is Associate Editor of the Journal of Biomedical and Health Informatics and also Associate Editor of Pattern Recognition. And this evening he's going to talk about research at the interface between computer science and medical image understanding. So Raya, over to you.
Thank you, Fred, and thank you for the BCS for the invitation. I'll start sharing my screen and hopefully that will work. Is that okay, Fred?
Yeah, that looks fine to me.
Thank you. So you've seen the title, so I actually won't dwell on that, but there's actually some additional information as well. So I'll actually be covering different aspects. I'll actually cover work that actually has happened over the last 25 years roughly, but I'll actually concentrate on specific parts of that. My interest originally started with breast cancer, and since then we've actually done work in prostate cancer and more recently in brain and lung cancer as well. And we've got an ongoing project with that. Clearly, if I go back 25 years, there wasn't a lot of deep learning happening yet. And so there's some traditional image processing techniques discussed as well. And I'll actually cover some deep learning and machine learning techniques as well, which we've actually all used for segmentation and more importantly, recently classification and staging purposes. So we're actually trying to help radiologists or clinical experts in understanding medical images and how they actually deal with them. Effectively, a radiologist would actually look at an image and then decide what kind of treatment would follow, and that has a whole range. So if we can actually assist the radiologist in doing that, then our job is successful as far as I would say. So we're actually talking about computer-aided diagnosis, but what does that actually mean? So how a CAD system might work. So these are two images, and these are synthetic images, and we've actually added some abnormality to that as well, so we actually know where it is. And in the distant past, we've actually done experiments with expert radiologists looking at images like this as well and trying to find abnormalities and introducing CAD and see how CAD actually helped them in detecting abnormalities and becoming better at their job effectively. So find the abnormality in this case. If we were sitting in an audience, then face to face, then I would probably ask somebody to actually point out what they thought was abnormalities, but we'll actually see how the system actually works today. So the notion is that, so there is a true abnormality there, and if I point to that or if I circle that area, then a clinical expert actually becomes better at finding those. So sometimes the clinical expert will spot them straight away. Sometimes they actually look at an area and are not sure, and then help a prompt from a CAD system might actually help them. In addition, sometimes radiologists actually don't spot something, and then clearly a CAD system draws their attention to that area and they might actually consider it after that. Some CAD systems are very good and will only point to the right things, of course. Those systems don't exist in real life, because in real life there are things like false positives and false negatives as well. So this would be a false positive. That's just a bit of background information or background image, and there's nothing wrong with that. But in this case, the CAD system actually found a bit of information there as well. Radiologists, clinical experts might be able to deal with this if it's at this level, but if a radiologist, clinical expert actually sees something like this, then the CAD system is actually not very useful to them, and it might even distract them from finding the right thing. So because they actually would spend a lot of time interrogating different areas in the image that actually they don't actually need to actually look at. And to put this in perspective, if you actually are doing mammography and you're a radiologist, then you might actually go through 200 cases in an hour roughly, and 200 cases is 4 images each. So you actually talk about quite a lot of images. Most of those are normal, and abnormalities are the exception. So we're actually aiming for something like this, and this would actually be good for a CAD system. And I've never actually developed a CAD system in my life that actually only does this. So it only finds the false, the true positives, and the rest is all pretty good. So there tends to be a trade-off between things. So the trade-off between things is a true negative, a true positive, a false positive, and a false negative. And these can actually be picked up by CAD systems. And so the CAD system would actually be like this. And so we're actually, true positives are good, false positives are less good, but a limited amount we can actually deal with. And some of the challenges that we actually deal with should be clear from this slide. So what we're interested in is finding different types of abnormality. And so there's 3 examples here. So a cluster of small blobs called microcalcifications. And the one in the middle is actually a well-defined mass. And well-defined is because its boundary is quite clear and it tends to be a rounded shape. And then we've got more difficult ones as well. And this is an obvious case of that. It's a spiculated lesion, which basically has a mass in the middle, and then it actually has spicules or linear structures emanating from that, and they tend to be more difficult to detect. Not if they're this size, then they're quite easy to detect, but they actually appear quite small as well, and then they can actually appear as distortions in the underlying tissue. What radiologists, or what clinical practice is at the moment, is that a radiologist will actually spot these, and then the radiologist will decide on should there actually be histology after this, in which case the patient is actually followed up. And most of the time, if there's abnormalities, unless they're clearly benign, then there is follow-up, and histology is the gold standard. And I'll talk more about histology later on because we've got projects around that as well. So that is the background, and clearly we've actually done some work on this in the past 25 years, and I've just given a short list for the record of the things that I'll actually try to cover in this presentation. So I won't go into much detail on all of these, but on some of these I'll actually dive into slightly more detail, but I'll actually cover a set of use cases, and I've got 5 use cases. So the first one will be on breast ultrasound. And then after that, I'll actually talk about mammography and breast histology, and then prostate cancer to actually be slightly more gender balanced. And then I'll talk about breast density, risk and boundaries, and microcalcification and clusters at the end. If I'll actually run out of time at a certain point, I might actually skip one of these, but the slides will be available, I assume, and the talk will actually just continue. So we'll see where we end up. So the first one is something that we actually started doing recently. So historically, we've been interested in breast mammography, which are X-ray images, but more recently, we've actually been started doing work on breast ultrasound as well. And breast ultrasound is used as a follow-up after screening. So within the UK, we've got a screening program, and women are invited for that, and they actually return there every couple of years to actually get a mammogram or mammograms done. And those are actually checked by a radiologist. As I said before, the majority of them, nothing is wrong with them, and they'll actually continue in the screening program. Some of them are followed up because there appears something abnormal in the image, and the follow-up can be different aspects. Ultrasound is sometimes used as the follow-up, and histology is sometimes used as a follow-up. So there's different options there, and sometimes women are re-invited for a mammogram and might actually get a sort of zoomed in version of a mammogram to actually look at a specific area, and all of that happens. So hopefully you can actually see that there's quite a bit of variation in breast ultrasound lesions. Some of them are really well defined. So if I actually look in this area over here, then the top left-hand image, that's a really well-defined abnormality. But some of the other ones, if I go to the other end of the spectrum, then on the right top-hand side, there is an abnormal region there as well, but it's actually sort of embedded within the tissue itself, and it's actually very difficult to actually spot. There's clearly variation in size, and with ultrasound you actually get shadows and you get other aspects as well, which makes it difficult not to only find the abnormality sometimes, but also to actually indicate what type of abnormality it is. And we're interested in both those aspects. So and I'll talk a bit about both those aspects as well. So the first thing that we actually want to do is we want to make sure that we actually find an abnormal region, and we actually we've developed different techniques for that. And we've got a straightforward solution for that, because effectively we've actually looked at a set of existing deep learning approaches and developed or adapted some of those specifically for breast ultrasound lesions. And we've actually done quite a bit of transfer learning, but also explored beneficial augmentation techniques. And in the process, we've actually developed large data sets as well. And not all the large data sets are from ourselves, but they can be a combination of what's available in the public domain. And I think at the moment we're actually just over 1,000 images for this, and that is deemed as a sufficient data set, at least for the things that we actually are doing. So using a set of existing deep learning approaches, slightly adapted, we can actually do quite well in detection. And so what you actually see here is, and I tilted the image by 90 degrees because then it actually fitted better on the slide. But effectively, this is actually from 4 different data sets in 4 different rows, and it's got different deep learning approaches in the columns. So on the left-hand side, I've got 4 original images from different data sets. All these examples are benign, and hopefully what you can actually see. And the other thing that you need to note is that the annotations, the truth done by a radiologist, are in blue, and what has been detected is in red. So you can actually see there's variation between the deep learning networks. Some of them are actually better at detecting things than others are, but we've also got a few networks that actually perform really well on these abnormalities, and the overlap between the detected region and the annotated region is indicated by the value underneath the images, or on the right hand side in this case of the images. And if that value is 1, then you've got a perfect overlap. To be brutally honest, anything that's above 0.9 is really good segmentation, automatic segmentation. Anything below 0.5 I would actually doubt. And as you can actually see, some of these networks actually perform poorly as well. So if I look at the 5th or the 6th column, then over here you can actually see a number of regions that actually have been detected that are outside the annotated region, and it's actually broken up the annotated region as well. So it's actually performing not that well. So these are actually a few examples where most of the networks did really well, but it's not all gold and happy things in deep learning life, because there are a set here as well where most of the networks actually performed poorly, and some of the networks actually didn't detect anything at all. And some of the abnormalities were not detected by any of the deep learning networks. So if I look on the bottom row, then there is an abnormality, and it appears in the corner of the image, the bottom corner of the image, and that has not been detected by any of the abnormalities. What we've actually found out since we've been doing this work is that some of the deep neural networks actually are very preferential for the size of the abnormality. And clearly that has something to do with the data that you're actually feeding into a deep neural network. So if it actually has lots of examples of large lesions, then it actually has a preference to detect large lesions. And in this case as well, the very small lesions where there are fewer examples of, it actually performs poorly. However, some of these networks actually still do pretty well on most of these abnormalities, even if they're difficult to detect. And there clearly is a preference for some of the deep learning networks to actually do well. And we've got recommendations around that as well. So this is actually very recent work, and we've been working on that. And if everything had gone okay, then this would have gone into a publication today, would have been submitted today, but we had some problems, so it will probably be tomorrow now. That's detection. That's actually identifying where the lesions are in the image, but we actually also want to do classification. And some of the classification is really simple. We can actually plonk in a whole image into a deep learning framework and have ground truth at the end, and that will actually give us some results there. And we've actually been doing that over the last couple of years, but also very recently. And I think on one of the next slides, I've got results that one of my PhD students actually produced. Was it this morning or yesterday evening? So this is all fresh and new research. So classification, some results. In green, in this case, it's a benign abnormality, and in red, we've actually got a malignant abnormality. And so the top row of images actually shows that all the networks that we've used for this were very good at saying they not only found the abnormality in the right place, but they also identified it as the correct class. So in this case, all benign cases. For the second row, we've actually got a malignant case, and that's slightly more, the boundary is slightly more complex. All the networks actually find the abnormality, might slightly under-segment it, but their classification is correct as well. And again, we've got two rows, a benign example in row 3 and a malignant example in row 4 that actually are not classified correctly. Some of the networks actually find bits of the abnormality in the right place and might actually classify part of it, but it also classifies other parts of what it has detected as incorrect. And sometimes it gets it completely wrong. It actually finds the abnormality in the right place, but it classifies it wrong. So this is actually an area that is interesting for us because this will actually determine patient treatment as well and what the follow-up might be. So at the moment we've got, for this specific study, we had a sensitivity of 87 for the benign cases and 61% for the malignant cases, which is not good enough. And so we wouldn't actually dream about actually using this in clinical life because that actually doesn't help the patients. As I said, we've actually done some other things as well, and recently we got 81% on a larger data set, the data set of 1,000 images that I mentioned before, and 81% is getting good. We actually need to further investigate that and see what the details are, but that's actually a good starting point. And clearly what we're doing at the moment and over the next couple of months or years is we are creating a larger benchmark data set. And because clearly for what people actually have found is that certainly for deep learning, the more images you actually use, the better your results tend to be at a certain point. And so specifically around size of abnormalities, we want to be more inclusive, but we also want to understand why things go wrong and why they go wrong. And so finding out deeper into the deep learning networks in the middle somewhere, what the semantic segmentation actually produces and why it produces that is actually a good thing. And we also want to improve our segmentation approaches because effectively we want to use the output from the segmentation to actually feed into classification approaches. So the two graphs at the bottom actually indicate for one of the deep learning networks that we've used how the manual measurements of an abnormality compared to the automatic measurements of the abnormality, and we get good correlation for that. So that is actually a step in the right direction, and it actually saves end users a lot of time because they don't have to annotate things anymore. They can rely on the detection of the CAD system. So that is what we've actually done for breast ultrasound lesions. And the next study is about mammography and breast histology. And what the challenge is here is we've got different modalities. So on the left-hand side, we've got a set of mammograms. And so normally 4 mammograms are taken in the first screening round. And on the right-hand side, we've actually got histology information from a biopsy that was taken from this breast. And what we are interested in is there a link between those two modalities? Can we actually use the mammography data on the left to actually infer what the histology would look like? And we've had a PhD project around that sort of finished a year ago. The research is still ongoing, and we're actually hoping to follow that up with another study in the near future as well. So what we actually got for that is we actually came up with a framework for that, where effectively we put in an unseen mammographic image, and from that we actually have a pipeline where we end up with not only the grading of the mammographic image, but also an estimation of what the histology might actually look like. And if we've got an automated system like this, then there might not be a need for histology anymore, and clearly this needs to be verified. But this is actually a significant amount of work, because if you look in this picture and you actually see a model in there or an ML, then that is actually a deep learning network that actually transforms one bit of the data into a feature factor, into a classifier indicated by C, or into the other way around, into an image again. So there are 3 models in here. And so we actually built these 3 models around methods like this. So effectively, we've got a deep learning approach where we actually put images and regions of interest in. And then basically the deep learning network actually extracts features, and it actually uses those for classification in benign and malignant. And that would actually give us one model in our overall scheme. This work is ongoing, as I said before. We did some initial work, which comes very close to what we want to do, but that actually needed some pre-processing of data and some slightly different approach to it all. So we've actually done quite a bit of work on segmentation of these images and picking up different aspects of that. And these aspects are basically things that an histology expert would actually find in the image as well. Basically, they would be counting small dots or larger dots, and they would actually take that into account in their classification. So we've actually been exploring a framework for image retrieval so that we can actually link specific mammographic cases to histology cases. And we've got a very simple training part for that, where we actually generate from the mammograms regions of interest. We've got a dense net that actually produces in what we call the abstract or semantic segmentations for that. And we actually use those vectors effectively to actually find abnormalities or find an overview of what a sample might look like. And that is actually put into the same format as we would actually do for histology. So we've got a direct link between mammographic cases and histology cases, and we can actually say that things are right or wrong, and we use again for that. So if I look at the next image, then how do we use that? We've actually got some information here where we actually have the same networks that we've pre-trained and the generator as well, and that will actually produce then a sample. What this actually looks like in the middle of our system is slightly different, of course, because we don't fully understand what's happening in the middle yet. But this is actually the representation in the middle. And if you've got an understanding of that, then that would be good. But what we're actually trying to do at the moment is we're trying to actually cluster these and get an understanding of how different types of abnormalities in the mammograms are directly related to histology types. And so we've got different clustering methods looking at that and see if we can actually link the clusters between each other. To actually be able to do that, and we've actually done experiments around that, And so for the retrieval aspects, we actually get an image retrieval, which is quite good from our point of view. It's state of the art if you look at what other people have done in comparison. So it's 71% at the moment, but that's clearly not good enough for us. And we actually would like to do better than that. We've got quite a few things up our sleeve that we are interested in developing from that point of view. And in the first instance, we are actually looking at more data in this case. So far, our experiments have been based on 100 matched cases, and this is difficult to get. It's quite an effort to actually get data out of the NHS, and you actually go through a process. So we've actually been lucky. We've been collaborating with a group of radiologists in Norwich that actually have worked with us for more than 20 years now. And recently we've actually added histology experts to that as well, who are actually annotating things for us as well. So I think we're actually being lucky, and 100 cases is a good starting point. But clearly for clinical evaluation, you need slightly more than that. We actually need to do slightly more on the pre-processing side, and that's actually one of the things that we are working on. But we're also interested in developing deep learning models that might be doing better here. And we've got quite a bit of experience from that with our ultrasound lesions and how they actually work. So we actually are hoping to actually transfer that knowledge into this area as well. And what we actually don't know yet is how these things are actually linked and how they actually are working together. So why one cluster of abnormalities in mammography is actually the same cluster as a set in the histology data is something that we don't fully understand yet, and we would like to do that. And as I said, with more cases, we can actually start doing clinical evaluation as well, which would be a step in the right direction to get this closer to patients. And effectively, if we can actually make something like this work, then it would actually mean that fewer biopsies are needed. And so biopsies in general, sticking needles into patients is seen as not a good thing, or if it can be avoided, then that would be good. So those are steps in the right direction from our point of view. Our next case study is balancing the gender a bit, because I will be looking at prostate cancer, and so that's the other half of the population. So challenge, we're looking at images like this, and this is a different modality. We're actually talking about MRI data here, and this is MRI data across the pelvis, and you've got different slices of that actually make up a 3D volume. And what we're looking for in this case is a segmentation like this. So we're interested in the outline of the prostate itself, the central zone of the prostate, but also the abnormality in this case, and the abnormality is indicated in white. Specifically, what we're interested in is if an abnormality is actually outside the prostate, or if it's actually confined within the prostate, because that actually determines what kind of treatment the male gets. So if it's within the prostate, they might actually take the whole prostate out. If it's actually spread outside the prostate already, that is less of an option, and they might be looking at alternatives like radiotherapy or chemotherapy. It's not uncommon to actually have things in combination, so one actually doesn't exclude the other. So we've actually been looking at this, and we've been very good some time ago at finding abnormalities and finding the outline of the prostate quite well. So that's actually something that we think we've more or less solved. We've got a shape-based model, so that's actually not shown here. I can actually go back to the previous slide. We've got a shape-based model that actually does the outline of the prostate in 3D and finds the central zone as well. So the light gray and the dark gray areas is something that we can actually find. We would actually still like to find, or a better estimation of the white, because the shape model wasn't capable of doing that. But overall, the 3D modeling is doing very well. So we said we actually wanted to know what's happening in the peripheral zone and in the central zone, and if those are actually abnormalities or not. And we've actually got a set of different tools for that we've explored over the last couple of years. The first of those is actually something that's really simple, and it's a Texton-based approach, which we just borrowed from some texture analysis people that have developed that in the past. And effectively, we actually provided with examples of benign and malignant tissue within certain areas of the prostate, and we built a library of that, or dictionary of that. So, and effectively, you can actually then feed in new samples, and the new sample is then either close to a benign case or a malignant Texton, and then it's actually classified. And this actually works pretty well. I've got 2 slides with example results on that, and hopefully that can convince you that finding things is okay. So it actually produces Texton maps. And so these are actually different, the gray levels indicate different types of Texton. And hopefully you can actually see that regions in the image are actually classified as slightly different tissues. And then if I do a probability map of the abnormalities, then, or of abnormal tissue, malignant tissue in this case, then I actually get images like this, where I've got a number of different prostates and different slices in the prostate, and they're actually annotated, and we actually find different areas within that. The orange is basically what the system has detected. The red boundary is where the abnormality, according to the radiologist, is. And as you can hopefully see, this is actually doing pretty well. We've got other approaches that are similar to that as well, where we've actually got also a traditional approach, or a more traditional machine learning approach, where we've got multi-parametric data effectively. So instead of actually looking at one type of modality for MRI, we're looking at different types of modalities for MRI, and we're actually extracting features from that, and quite a few features. So lots of features go into a network like this, but this is actually very good at determining benign versus malignant as well. And some of the results. So this actually goes into a straightforward machine learning approach, and we've actually used different machine learning approaches for this. But as from that point of view, the interesting bit from our point of view is actually in the parameters that we extract from the images that are linked to different aspects that we expect the abnormality to be responding to. So, and as you can actually see, again, a similar approach where in red, a red line actually indicates the abnormal region indicated by the radiologist, and what we've actually detected with a color map, a heat map, is that we actually do pretty well, and we actually get good area under the ROC curve here, and we're actually, these are actually very good results from that point of view and state of the art. More recently, because effectively what we've actually done with those results is we can actually combine the different segmentations into one overall segmentation, and we've recently started using deep learning methods in there as well. So we've actually looked at a set of deep learning approaches, but we've actually done augmentation slightly differently. We've looked at augmentation using superpixels and adding noise and blur. And we had 2 visiting researchers over the summer, well, 2 summers ago and a year before, and they actually looked into this, and they actually did evaluation of this, and they actually found as well that they've got pretty good results overall. So we've actually got results that actually show that the segmentation is really good, and that we actually get good results in this for different modalities, and it actually finds things pretty well. So this is not classification, but segmentation. So that's gone full circle. What we hope to do over the next years is to actually continue with that trend of using additional modalities, but also further explore deep learning approaches and combine segmentation results. Bottom line for us is that we would like to use the segmentation results, and specifically the benign malignant segmentation results, to actually do staging of cancer. So how aggressive is a prostate cancer? And that actually informs treatment. So that is the way that things are actually going for prostate cancer at the moment. And that is what we actually are making our contributions to as well. if I go to my next case study, then I'll actually be looking at breast density and risk and boundaries and aspects like that. So breast density is one of the indicators of risk in mammography. So the notion is that if you actually have less dense breast, like on the left-hand side, then you're less likely to develop breast cancer. While on the other hand, if you've got dense breast, like on the right-hand side, you actually have 20 times more likelihood of developing breast cancer. Added to that is that, hopefully you can understand this as well, that if you've got an abnormality in the left-hand breast, then it's easier to spot than you have the same abnormality in the right-hand breast. So there is different sort of scoring systems for this, and there's different ways of actually using this bit of information as well. So we actually want to classify images into different categories, and that can either then be used to indicate what kind of further processing is needed, because you might actually have a lesion detection approach that is actually dependent on the density of the breast, and you might have, in this case, 4 different models. So if you find one that is less dense, then you apply one model. If you find an image that is really dense, then you might apply a different model. All this information can actually be used to change how often women are invited for screening. So if you are less risky, then you might actually come back in 5 years' time. If you are high risk with a high dense breast, then you might be invited within a year or 2 years again. And so that actually informs how patients are treated again. One of our original approaches to this was really simple. We basically did a very simple segmentation of the image into dense and non-dense tissue. And this is actually after pre-processing the image by finding the breast area first and the pectoral muscle, which is the pectoral muscle is effectively the muscle in the top left-hand corner of the image. And so those are first removed, and then we actually are left with the breast, and we did very simple segmentation, very robust segmentation as well. We use different approaches for that, and one of the more successful ones in that is a fuzzy k-nearest neighbor approach, or a fuzzy clustering approach that actually works really well here. And effectively, we extracted lots of features from the 2 areas that were segmented. So from the gray and the white area, basically we looked at features that were from a morphological and texture features, and those were used to actually classify images. Classification works really well in this case. We've actually got, for one of our data sets, standard data sets, a success rate of 91%, and for another larger data set, we've got 86%. The added benefit of this is that the confusion, if I look at a confusion matrix, then it's only 1 class out at the most, which is actually a good result from our point of view. We've actually, since then, we've actually been looking at some other techniques as well, where we've actually looked at more detailed segmentation. And the detailed segmentation is sometimes based on density, as it is in this case. And it's actually picking up different aspects of dense tissue. So it's actually finding linear structures in the mammograms, but also larger blob-like structures indicated in blue, and some other aspects as well. So this information can be fed into a classification model as well by just looking at the different proportions of the tissue that you've got in this case. And we've got another representation of that as well, where we've got some slightly more modern images, which were digital. And so again, we actually classify things according to different tissue types in this case. And tissue types in this case were determined by an expert radiologist. We've done quite a lot of other things in here as well. So we've actually looked at blob models, for instance, where basically we've got a blob representation of the mammograms, and that actually works really well as well. In all of this, we've actually gone, so this work actually started with segmentation of the pectoral muscle and the breast itself, but more recently as well, we've actually come back to that and used very recent techniques to actually do segmentation of the pectoral muscle in this case. And that actually has improved our overall segmentation. So if you've got a better starting point for these things, then in general, your results actually improve as well. So that's one of the reasons why we actually went back to looking at these more traditional segmentation aspects that are sometimes very difficult to actually find. And we've actually used recent deep learning methods for that. In addition for that, we've actually, in collaboration with some other people in the department, we've actually looked at sort of fuzzy, rough segmentation techniques as well, and doing image improvement, and that actually improved things significantly as well. So even with a very simple set of features, which normally would only provide you with just a below 70% correct classification for a large data set, that would improve to 94 by improving the image quality, in this case by using fuzzy rough sets. So this is actually a good thing, and clearly having a classification of images is beneficial for screening programs, but also for other CAD systems, as I indicated before. So one of the things that we are interested in from this point of view is how much do we trust risk assessment in this case? What kind of confidence do we actually have in the segmentation and in the results? And that's an active area where we are actually looking at. And that is actually providing us with new insight in how radiologists actually perform these tasks as well. Large-scale evaluation, you might have actually noticed the trend in some of the slides here, is something that we actually do as well. The other thing that we actually want to do is, from a deep learning point of view or from a machine learning point of view, is have an understanding of the semantic segmentations that we actually are getting. So why does it actually segment certain aspects of the image, and how does that actually benefit us in understanding what we're actually doing with these approaches? That actually brings me to my final case study, where I'll be looking at microcalcification clusters. So the challenge in this case is actually finding small clusters of small blobs in large mammographic images. And there's two aspects in here: finding them first, and then the second step is to actually do classification of these. Finding them, we actually are very good, and other people in the world are very good as well in finding these small blobs. They actually are well defined. They've got nice boundaries, and there are now a number of different methods out in the field that are actually used for this. And if you've got top-rated methods, and this is actually one of them, which is basically a very simple filter bank approach that we developed several years ago, and using traditional techniques, machine learning techniques, to actually produce probability images. These are as good as a radiologist is, and will actually find 99% of the abnormalities in this case. What is actually is slightly worse at is classification, and I'll talk about that later after I've actually shown some results. So these are actually detections results. They're slightly faint on the right hand side, but they actually are finding the right blobs in the image and actually indicating where they are with great precision, and they actually don't miss an awful lot of them. So, and this is actually the starting point for what actually is used for classification after that. And for classification, again, we've actually used different techniques. One of the more interesting from our point of view is something that is actually based on the topology of the microcalcifications in the cluster. So how close are they together? How are they connected to each other? And we've actually developed a very simple approach for that. And effectively what we actually do is we actually dilate the microcalcifications in the cluster and then see when once they're connected, and base graph generation on that. And I'll actually show you slightly more examples of that in a minute. And then basically what happens with those graphs is we extract a set of features from that, and those are actually used, again, using traditional machine learning techniques to actually determine if something is benign or malignant. And this is a simple framework, but it works really well, and I'll show you that. So hopefully what you can actually see is that if I do modeling at scale 1, 8 or 32, I get different networks. In addition to that is hopefully what you can actually see is there is a difference in appearance between the graph at the top and the bottom. One of them is benign and the other is malignant. And that's exactly the information that we are exploiting here in the image classification or the classification of the abnormalities. What we're actually getting here is results that are better than 90%, 95% correct classification on large data sets. And we're very happy with that from that point of view. We've got slight variations on that as well. So we've actually looked at some other aspects around this and how things are connected and how we actually measure things. And we've done a set of publications around that where effectively we extract different features around the connectivity of small blobs in clusters. And again, this actually works really well. Slightly, I think, just below 90% in this case, classification results, but also very interesting because it shows us more insight in why things are classified, because we've got a richer domain here of features, and that actually has worked really well as well. So in detail, hopefully you can actually see slightly different appearances between the benign and the malignant case, where some things actually happen over different scales for the malignant that actually don't happen on that scale for the benign. And that's exactly the information that is used in classifying these cases. So what we actually are working on at the moment is not on the detection side, because as I said, that is actually as good as top radiologists actually are, but on the classification side. And because classification, although it is above 90%, is not as good as histology, because histology doesn't make any mistakes apparently. We are looking at how you can actually, to what extent you trust this and what kind of confidence levels we actually need in that. In addition, over the last couple of years, we've been exploring tomosynthesis, 3D aspects. So tomosynthesis is effectively a 3D version of mammography, and we can actually model the microcalcification clusters in 3D now, and we can actually see how they actually are connected in 3D as well, and extract interesting features in that space and see how that can actually be used for classification results. We've only recently obtained a large data set from somewhere else in the UK that actually contains lots of cases around tomosynthesis, and we're investigating that at the moment. Those were my 5 use cases, and what it actually leaves me to do is actually thank a lot of people, because clearly I haven't done this work on my own. So the first group of people are ex-PhD, current PhD students, postdocs, and international collaborators from across the world. And so some of these are still with us at the moment, and some of them actually have moved on to different parts of the world. Some of them have gone back home. The second group of people is very important to me as well, because these are our clinical experts, and they actually have contributed significantly to the work, because we discuss initially problems that they actually have within their field, and we actually are looking for solutions. They also provide us with annotations, and they're involved in the evaluation of things. And then finally, there's a list of people I can't do without, because they actually provide funding for us, and there's lots of them. And so that's a whole host of people I would like to thank, because without them, this presentation would not have been possible. Which actually leads me to my last slide, and I presume Fred might actually want to come back in at this stage, because I think there might be the option of questions.
Yes, indeed. So thank you very much, Raya.
Do you want me to stop sharing at this point?
Yes, I think so. And then if people have questions, they can type them into the chat, which you should be able to find. If you just move your mouse over the screen, you should see a chat icon. and then you can, as I say, type a question into the chat, or you can also raise your hand, which is under the reactions icon. So do we have any questions? There is a question. What do the holes in breast ultrasound lesions represent?
So the holes are basically abnormalities, and they can be cancer. They can be other abnormalities as well. So you've got cysts in breast as well, which are clearly well-defined abnormalities. So I think one of the examples, if I remember correctly, the top left-hand corner was a cyst, while some of the others were actually cancer. So you've got different approaches, but you've got normal tissue as well that sometimes actually looks like a lesion. And so there is confusion as well from that point of view. And that's one of the reasons why the systems that we've actually developed find false positives. The system is not always clear, and radiologists find false positives as well, by the way. So
could I ask just how much computing power do you need to run some of these studies?
So initially, if we actually start off with a project, very little, because we basically run things on APC to actually find out if something is working on a small data set. Then we tend to scale things up to the GPU cluster that's within the department. And I don't know how many nodes that actually has at the moment, but it's never enough. And then the next step for most of my PhD students is to actually use supercomputing wheels or something equivalent to actually run things for larger evaluations. And then it's actually doable. So instead of actually waiting for days, then you actually run things in an hour or something like that. There are things that I presume will actually be pushing the boundaries around that as well anytime soon. So I mentioned 3D tomosynthesis data. There's lots of information in there, and we can actually, that actually takes up quite a bit of processing time as well. So, but we can actually run all of that in parallel, which is a good thing, of course.
Okay, another question. What kind of accuracy is good enough to be clinically useful? You mentioned 81% accuracy on one slide. Is that better than human experts can do?
That's very much depending on what kind of application area you're talking about. Sorry. For some of the application areas, we actually think 80% is actually an improvement on what a radiologist, a clinical expert can do, in which case it gets used in a clinical domain. As I mentioned, in some other cases, you need to be 99% correct before it actually comes close to a clinical expert. But there are systems out there that will actually do that as well. So it's very dependent on what kind of application area you're talking about. And in general, clinical evaluation actually takes a long time to actually get it from research into the clinical domain. Can take 5 to 10 years before the software is actually validated, etc., and tested sufficiently.
These figures are just on the accuracy, but presumably also important is sort of the rate of false positives versus the rate of false negatives.
So what we have in general from a clinical point of view is we actually do ROC curves, which are basically a trade-off between false positives and false negatives, true positives and true negatives. And what we're interested in is actually doing that over larger data sets. And one of the metrics that we're using is the area under the ROC curve as an overall figure for a system. And that is something that we're working with most of the time. If you've got an ROC curve, then basically you can actually determine yourself where you want to be on that ROC curve, how many false positives are acceptable. And that's a trade-off with the number of true positives you actually get then.
Question, yes, similar. Would you prefer to be having more false positives or false negatives?
I think that's actually, as indicated a minute ago, if you're looking at an ROC curve, it's a trade-off between things. So most of the time, if one goes up, then the other goes down. In general, false positives Depending on how critical it is, false negatives are really bad because missing things and saying that somebody hasn't got anything wrong is seen as a really bad thing. False positives, a lot of the false positives we can actually explain. And so in the most modern systems, you actually get probabilities next to the abnormality as well, indicating of how certain the system is about what it actually is and how it actually deals with things. So I think that's actually a field that's developing rapidly at the moment with deep learning aspects in there. And the next question is, what side of data sets are useful for building the models? So as I said, some of the models are actually based on 100 samples, and some of the models are based on 1,000 samples. What we actually do find is that the more variation that you actually have in the abnormality you're looking at, the more data you actually need for it to actually get robust models. As I indicated for the ultrasound data, that was or that is lacking in smaller size lesions, and those are underrepresented in the data set. So it's actually performing worse on those than on the larger lesions. And so the balance is to actually get the right data set. So my assumption would be that adding large lesions to the data set wouldn't help, but actually adding a few small lesions to the data set would actually help significantly. So, and I think that's actually what we're actually looking at the moment as well. So how can we make things more? And then the next question is, how long before AI makes clinical decisions without human intervention, or will these tools only ever augment the effort of clinicians? So we actually see CAT tools, computer-aided diagnosis tools, as additional information for clinicians to make decisions. I wouldn't want anytime soon to actually have an AI making clinical decisions without human intervention or without possible human intervention. So we've got screening aspects. And so, for instance, one of the ways that density estimation is actually used is to actually inform you about which patients might actually, or which women might actually have less probability of developing breast cancer, and that is actually used quite effectively. So it depends on what kind of decisions are made as well. All the things that we've done, as said before, are with a clinician at the end point who actually makes the decision and uses this information.
Okay, thank you. Are there any more questions? No, that seems to be it. So thank you very much, Raya, for a very interesting talk. And thank everybody for attending. I hope to see you at future BCS Mid Wales branch webinars. Okay, thank you and good evening.
Thank you, Fred.